Let's now capture and make measurements on this RF pulse train. I'm going to press single. You'll see I'm actually pulling in a large number of pulses into segments. I've defined 8,000 segments, 8K. The scope brings up a picture of the first pulse. I'm seeing a number of things here. I've defined a math function, which is the envelope, and I've dropped a measurement onto that of width, and I'm seeing a 3 microsecond measurement. I also dropped a frequency measurement inside of the pulse, and I'm measuring 2.51 gigahertz at that point within the pulse. I've defined a math function which draws a trend across the pulse, showing at each cycle across the pulse what is the frequency measurement. And I've defined an FFT math function so that I'm looking with a center at 2.5 gigahertz and about a 200 megahertz span. If I walk through a few of these pulses, there's segment 1, here's segment 2. Notice the next pulse is wider, it's almost 4 microseconds. Notice the frequency dropped, it looks like it's a little bit less than 2.4 gigahertz. And if I look at the measurement in the FFT, I'll see that this first peak is in fact 2.42 gigahertz. And if I step on through a few more of these segments, each segment holding one pulse, you can see how the frequency is jumping around pulse by pulse, and I'm also changing the pulse widths. So I've been able to make a very long capture. In fact, if we move to the end of all these segments, you'll see that this is 8.2 seconds worth of capture accomplished by using this segmented memory.